Welcome to today's lecture. So far we have got a basic introduction of composites. So we have seen what composites are. They are made of two or more materials, and we have seen that the kind of composites that we are going to deal with, they are mainly in laminated form. We have seen the constituents and we have seen how we can make them, what are the fabrication process, and also we have discussed about the applications. Now this course mainly deals with the mechanics of composites. First we will formulate the mechanics of the composite plies and then laminates, and then we will do analysis of these laminates. So these will be mostly laminated plates. Now while this analysis mainly involve solving some differential equations. So every laminate will have its own governing differential equation and set boundary conditions, and we have to solve it. And by doing that we can find out the displacement, strain, stresses in the laminates. Now it is not always possible to come up with the closed form or analytical solutions of these differential equations. So for that the more robust technique that we have is through the application of energy or virtual work principles. So it is to keep the course self-contained, we will spend some time in understanding this energy and virtual work technique, and we will do that through the example of a simple structure, not a laminated structure. So a simple one-dimensional structure that we can think of is a beam. So if you have a beam like this, and the beam is under some transverse load, and let us say this is x and z, then we know that this follows a governing differential equation, and the differential equation is del 2 w by del x2 into of EI into del 2 w by EI into del 2 w by del x2. This entire quantity is differentiated twice with respect to x, and that is equal to the applied load Q. And there are some boundary conditions at this is at x equal to 0 and this is x equal to L. So here at x equal to 0 we have W is equal to del W by del x equal to 0, and at x equal to L we have the moment equal to 0. So del 2 W by del x2 EI equal to 0, and the shear is also 0. So del x of del 2 W by del x2 equal to 0, and that is at x equal to L, and these boundary conditions are called essential boundary conditions, and these are called natural boundary conditions. Now when the problem is simple, the Q has proper distribution along the length, and the stiffness the beam geometry or the material properties E, they do not abruptly change along the length, we can get a closed form solution of this equation. But when that is not the case, it is difficult to get a closed form solution, then we go for energy or virtual work method based solution. In case of laminated composites, even with a regular geometry also, it sometimes may be difficult to get a regular closed form solution. So depending on the sequence of the plies are put, or depending on the boundary condition, there can be cases where we cannot have a analytical or closed form solutions. So at that time an energy or virtual work based equation method helps us. So we will understand this method with the example of this structure. Now before discussing energy or virtual work based method, we need to spend some time in understanding variational calculus. because that is a very powerful tool that is used for these techniques, variational calculus. So, let us say that we have a function of x, something like this, and then we just perturb the function little bit, and get a variation like this. So, after perturbing little bit, the function, new function is this. So, the initial function is f x, and this new function is f x plus delta x. So, sorry, not x plus delta x, it is f x plus delta f x. So, it is f x plus delta f x. So, the difference between these two functions, that means the amount of perturbation we have done, amount of variation we have done, that is basically delta f x, and this delta is called the variational operator. So, f x was the original function, we did some variation of it, some perturbation of it, the amount of variation was delta f x, and then the new function is f x plus delta f x. Now, this variation has to satisfy a constraint that wherever I know the value of the function, I cannot do a variation, because the value of the function is fixed there. So, I cannot change it, I cannot vary it. So, say in this problem, at some x, say this is x1. So, at some x we know the value of the function, in that case at that x the variation should be 0, that means the value should be same here, the blue function, the black and the red function value should be same as at x equal to x1. So, if value of f at x1, that is f at x1, or to be more precise, f x defined at x1 is known, then variation at x equal to x1 should be 0. Now, in our context, when we analyze the structure, our solution variable is this displacement W, or in case of a laminated plate, we can have displacement component in different directions. Those are our multiple solution variables. So, those solution variables are our function f, and then through essential boundary condition we may know the value of the function at different points. So, at those points variation of those solution variables is 0. So, here for example, if I take the example of this, at x equal to 0 the variation of W should be 0. So, the variation should not violate the essential boundary condition. Now, this variational operator has some properties. First of all, if I have two functions f and g, and then if I take their variation and add it up, that is equal to taking the variation of f plus g. So, this is delta of f plus g. So, if I take f plus g and do its variation, that is same as taking the separate variation and adding it up. Similarly, variation of f minus variation of g is equal to variation of f minus g, and then if I have two functions f and g multiplied and they are take their variation, that is equal to variation of f multiplied by g plus f multiplied by variation of g, and from this we can write if f is equal to g, then delta of f square is equal to twice f delta f, and then we have, if I divide f by g and take variation, that is equal to g into variation of f minus f into variation of g divided by g square, and also we have variation of del f by del x is equal to the derivative of del f. Similarly, if I integrate a function f and take variation, that is equal to taking the variation first and then integrating. So, these are the properties which will be very useful for us. We will frequently use these properties when we do energy or virtual work based analysis. Now, let us understand the principle of virtual work. So, for that, let us consider a 3D body, an arbitrary 3D body, which has some supports and which is under some loads. So, there are loads P1, P2 and all the way up to Pn. Now, under these loads the body deforms, and the deformed shape may look like this. Suppose the deformed shape looks like this. The red color means undeformed body, and then the black color means deformed body, and let us use another color. Say this blue color is if I do some perturbation of the over the deformed shape. So, let us perturb the deformed shape little bit, again and again. It is understand it is not a real displacement or something, it is something virtual, it is in our consideration. Again the red color was the undeformed body. So, when it went from red to black, that means some amount of deformation happened, and those deformation has components along x, y and z, and let us call those components u, v and w. U is deformation along x, so u is displacement along x, v is along y, and w is displacement along z. And then we said that on top of the deformed body on top of the deformation we did some additional perturbation, we gave it additional deformation. That is not real, but that is our consideration, that is why it is called virtual. And that quantity, let us define that as we define that quantity as the variation of u, v and w. So, u, v and w are functions of x, y, z. So, their variations are also functions of x, y, z. Now, this variation, as I said, the variation should be 0 where we have the essential boundary conditions specified, that means the values are known to us. If I look at this structure, at these supports that we have, at these supports we have the values specified, that means at these supports the support does not move. So, at this support there cannot be any displacement, that is why the perturbation also is 0 at the supports. It would have been possible that the supports has some specified amount of displacements, so that in that case the black curve which signifies the deformation or displacement would have some value there, the specified value, but the blue curve would have value 0, that means the difference between blue curve and black curve would be 0 at the at that point, although the specified value is non-zero, but the variation has to be 0 there, that is the condition. Now, we define something called external virtual work. And the external virtual work is the amount of work which I can attribute to the force due to the virtual displacement, not due to the real displacement, due to the virtual displacement. That means from the deformed shape to the undeformed shape, the amount of displacement that is there, that displacement multiplied by the force is our virtual work done by the external force. So, the external force may have components x, y, z. So, P1x is the component of external force 1 along x direction. So, that multiplied by delta u at 1, at that point 1, because u is the displacement along x direction, plus P1 y, that means component of P along y direction, that multiplied by delta V1, V is the displacement component along y direction, and V1 means at that point, plus P1z into delta W1. Similarly, at point 2 we have P2x into delta U2 plus P2y into delta V2 plus we have P3z into delta W3, and it goes on up to the nth force, the last force Pnx into delta Un plus P1y into delta Vn plus Pnz into delta Wn. So, that is the total amount of external virtual work done by the external force. Now, during the virtual displacement there can be additional strain also, and that we call virtual strain. So, that corresponds to some internal work also. So, there is a stress when the body is in equilibrium, stable equilibrium in the deformed shape under the action of the external forces and also with the boundary conditions. So, the body is already having some strain and stress, that stress is the real stress, and then from that deformed shape when it goes to the additional deformation, I mean when it goes through the virtual deformation, some additional virtual strain comes, that we call virtual strain. So, that the original stress multiplied by the virtual strain is called the internal virtual work. So, now let us define something called internal virtual work. And internal virtual work is equal to sigma xx multiplied by, so we know sigma xx is stress along direction 1, normal stress along direction 1, multiplied by the virtual normal strain along direction 1, that is the internal virtual work corresponding to this xx. And that when I write like this is work density, internal virtual work density. If I integrate over the volume, that would give us the total internal virtual work, but that is corresponding to only one component. So, there are 3 normal components and 3 shear components. We will look into these stress components in more details as we go along. So, if I write it for all the stress strain components, we have this. So, we write the virtual work for each stress strain component and then add them up. And that is the total internal virtual work. And the principle says that, the virtual work principle says that the internal virtual work should be equal to external virtual work. So, internal virtual work is same as external virtual work. So, this is the virtual work principle. Now, we can understand the virtual work, internal virtual work little bit more with the help of this diagram. So, let us just assume a typical one dimensional case where we have epsilon xx and sigma xx, and let us say that other quantities are not there. So, the stress strain variation is something like this. The material can be linear, isotropic, whatever. So, even if the material behavior is not linear, that means the stress strain behavior is not linear, the principle still works. And let us say that at this value of stress and strain, this is the value of stress and strain at which at the deformed state. That means at this value of stress and strain, the entire body is in stable equilibrium. So, the amount of external work done by the external force has been stored as the internal energy or the strain energy in the body, and at that point our strain is this much and stress is this much. This is signified this point. Now, we are saying that we are artificially giving some additional deformation. Now, we do not bother about the source of the deformation, the cause of the deformation, that is a virtual. So, that is our just consideration. So, that is virtual, and during that deformation the amount of strain is this. So, after this additional deformation, the virtual deformation, this is the amount of strain. So, if I draw a rectangle over here, so the area under this is our internal virtual work. So, this is our internal virtual work. Now, let us understand something called the principle of minimum potential energy. So, in this case, if we look at the same example that we had in the diagram, we have a body, arbitrary 3D body under some loads. In that case, we find out something called total potential energy of the structure. And that total potential energy of the structure consists of U, that means the strain energy, minus the work done by the external load. So, this is total strain energy and this is work done by the external force. Now, this entire quantity minus W, W with a negative sign, is also called potential of the applied load. So, if for this particular case U is going to be, so pi is, so U is going to be half multiplied by stress into strain is the strain energy density, and then if I integrate, that becomes our total strain energy. So, if I consider all the components, the total strain energy is half into sigma xx into sigma sigma xx into epsilon xx plus half into sigma yy into epsilon yy, and we do it for all the components. Plus half into tau yz into gamma yz. We integrate this quantity over the entire volume, that is the total strain energy, and work done by the external forces we have seen P1x multiplied by U1 plus P1y multiplied by V1 plus P1z multiplied by W1, and we do it for all the force components. And the principle says that the total potential energy we generally denote as capital pi, and the principle says that the variation of the capital pi should be 0. If it is 0, it indicates that the body is in equilibrium. Now, it may correspond to two cases. When the variation is 0, it is basically an extremum. So, extremum means it can be minimum or it can be maximum. So, let us bother about the minimum first. So, it means that due to the applied force, there are different possibilities of different possibilities of deformed shape being created, but out of those it choose that deformed shape at which this quantity pi, which is basically a combination of u and minus w, should be minimum. So, this resembles that pi is extremum. So, an extremum can be minimum or maximum. Okay. So, minimum or maximum. So, when minimum it denotes stable equilibrium. So, for example, in this case we have applied the load on the structure, and under that load the structure is deformed, and in this black shaped configuration it is under stable equilibrium. That means the total potential energy is minimum. If maximum, then unstable equilibrium, an example of this is buckling. So, in this course we will do both the analysis for both finding out the deformed shape under load. In that case we will seek the stable equilibrium, and also we will do buckling analysis when we will try to find out the unstable state of the structure. In that case we will try to find out, for the buckling problems, in that case we will try to find out the unstable equilibrium. So, in both the cases we can follow this energy or virtual work based approach. So, we have to calculate pi and set the variation to 0. Now, these potential energy or the virtual work based approach are also related. So, in the next class we will take the example of that beam, and we will see that they are related, and then we will see how using this approach we can find out a stable equilibrium solution of a structure. So, this would just give a background of this method, and then we will extensively use this method when we start analyzing the composite laminates. So, this background on the energy or virtual work principle will be helpful in week 6, 7, 8 and 9. So, this brings us to the end of this lecture. Thank you.